Good evening and welcome to Season 3, Episode 5 of the Late Night Conference. My name is Wilhelm Huck and I'm your host tonight. And I'm delighted to see people in the live audience here tonight at the Huygens building of Radboud University. It's a very warm and sunny evening, so we have some competition tonight. And I'm also thank you for the people who are watching online. So in the past sort of episodes this season, we have been exploring the relationship between chemistry and AI, or at least some of the opportunities that will be available when we looking at AI and machine learning and see if we can translate that knowledge that we have on chemistry into some kind of machine learning version. And tonight's speaker is somebody who has really gone beyond what everybody else is doing, who has been really sort of looking at transformer-based large language-based models to see if we can sort of teach them how to understand chemistry, which is really a step sort of in a different direction from previous episodes. Our guest tonight I'm talking about is Dr. Teodoro Laino, a distinguished research scientist at IBM Zurich. You can see him on the screen behind me. Theo is a computational scientist, computational chemist, I should say. He did his Master of Science in Pisa in 2001, followed by a PhD in 2006 on quantum mechanical calculations and ab initio molecular dynamics with the guru, I should say, of computational chemistry, Professor Michele Parinello. So he's really well versed in that field, but then decided after a postdoc with Professor Jörg Hutter at the ETH Zurich to really make a step towards sort of AI and industrial applications of AI. We can discuss that later on as well. In 2008, he joined IBM Zurich, where he has been ever since. And he really made enormous big breakthroughs, as I mentioned before, in using molecular transformers in synthetic chemistry, so designing molecules, but also in biocatalysis and many other fields, as I'm sure he will be talking about very shortly. So Dr. Laino, the floor is yours. We look forward to your presentation.
Thank you so much for the very kind introduction. Really, it's a pleasure for me to be with you, even if remote only, and I hope there will be still plenty of time afterwards to enjoy the nice weather. Absolutely. So it's a great pleasure again to be here and talk a little bit more about language models. And of course, I would be completely unfair if I wouldn't be starting by recognizing the real people, the people that have been doing and that keep doing all the work behind what I will be presenting today. I'm sticking my face, but without them, I probably wouldn't be here talking about the work that we did in the team, both current members, but also former members. And among those ones, of course, I have to highlight Philip, that is nowadays an assistant professor, tenure track at the EPFL. All these things started with him and with Theophile almost 5 years ago. So large language models, transformers, I think is important to give a little bit of context without spending too much into the mathematical details. So keep it as an inspirational presentation on language. Maybe if you're curious, I mean, there are plenty of other resources where you can find more in-depth details. And for what is interesting for us in the next 30 minutes, it will be important just to contextualize what are language models. I mean, in general, language models are, we can consider them like mathematical objects, relatively black box, that are taking as an input some text and that can perform two different types of operations, producing in output some text. So this is the first class of language models. or producing in output a numerical representation of the input text. Now, some examples. I would have loved to be there on the stage, and talking with you, but I'm sure that, and ask this question in person, but I'm sure that many people know exactly an example for text input, text output. Examples like ChatGPT is a very straightforward one of language model that can generate text based on prompt text. For the second class, the one that are converting input text into numerical representation, there are several applications, although some of those are not really practical, because in general, we as a human run away from multidimensional vectors. But in general, you are experiencing those type of language models extensively, even during daily operation. Even when you do web searches, you have models that are actually converting the entire sentence into a numerical representation for then performing mathematical operations. And now the other important thing is we are talking about chemistry, but why are we mentioning language? Because language, in essence, and this was one of the earlier definition that I was able to find, 1921, almost 100 years ago, so not too much back in the past, was defined by a non-intrinsic way of communicating ideas by means of voluntarily produced symbols. And of course, if you are considering a chemical protocol or a description of an experiment in English, in natural language, I don't think that anybody has disagrees on seeing this paragraph as a representation of a language. But what if I would tell you that the same paragraph can actually be represented with a slightly different language, a language which is domain specific, that is not natural, has been created by humans, but exactly with the objective of communicating knowledge through voluntarily produced symbols. And so in this case, we are using the Marcus representation. We are using letters for identifying atoms, and we are using bonds, double bonds notation, aromatic rings, and so on, charges, arrows, for providing an information to the person that is interpreting the chemical reaction. And the information that we are providing is the chemical reactivity that this transformation is containing. And of course, both in the context for what we will be observing in the next minutes, both type of language will be essential for putting together a mechanism that is leveraging machine learning, AI, more generally, for performing one task, the chemical synthesis of a target molecule. And so this is important. So the assumption is that you have identified a target molecule that you would like to synthesize. You can do that with generative models, for instance. And of course, you have to come up with a way that allows you to have that molecule physically in a vial, maybe a few hundred milligrams of that molecule, or even a few tens of milligrams of that molecule, for testing, assessing the effectiveness, maybe in vitro studies. And of course, how can we relate a molecule with its synthesis? There is one very simple way. Quantum mechanics is governing the entire space of chemistry. I think there was a quote by Pauli almost 80 years ago that said that chemistry is a solved problem. We know all the equations that are governing chemistry. The only problem is to solve those equations. And of course, coming from a background in computational chemistry, quantum chemistry, It's very fascinating, and it's very inspiring to think that with quantum chemistry you can really design the intrinsic element of a chemical synthesis. However, the complexity is still quite big. And while we are developing technologies, we are increasing the computational power, we are developing new architecture for doing calculations like quantum computers that are more natively prone to address quantum problems like quantum chemistry. We are still quite far from solving real practical problems in the space of the chemical synthesis. And the reason is that you need to perform lots of sampling. So Baker, where a reaction is running, is made up of 10 to the 23 molecules that are basically going around and that you have to sample in order to represent the right reactivity. And so we will not be covering quantum chemistry. We will be exclusively relying on data that has been published for every single chemical reaction reported, for instance, in articles, in patents, or in technical documents. So the assumption here is that what we are observing in an experiment is actually matched by the underlying physical equations that are governing the system. So in a certain sense, using the natural language description of an experiment is a way to shortcut completely the solution of the Schrödinger equation for addressing a specific problem, especially if you do that in a context where the data is very rich and where you can have a meaningful statistical description of the chemical transformation. Now, let's start deep diving. There are two steps that we will be looking in the next slides. The very first one is the one of the design of the synthesis. In organic chemistry, this is also called retrosynthetic analysis. And the second step after the retrosynthetic analysis is actually the synthesis execution. So you have to take the every single reaction that has been recommended by the retrosynthetic tools, and for each of those reactions, you want to compile a very detailed experimental protocol that either a person or, in our case, a robotic system can actually execute in the lab. Let's start with the first one. And instead of jumping directly into the retrosynthetic analysis, I will be first addressing one problem which is a little bit easier from a mathematical point of view, and is the problem of the forward reaction prediction. So the forward reaction prediction is stated as a problem that, given a set of precursors, two or more precursors, what is the most likely set of products that will be generated by the chemical reaction between the precursors? And of course, this was where we had the inspiration. Philippe Théophile had the inspiration back in 2017. If you think that arrow like a way of converting a certain sequence of characters into another sequence of characters, what type of technology does this recall to you? You have a sequence of characters. Let's say that they are transmitting some knowledge. Maybe they are in English. And you are converting this sequence of characters into another sequence of characters that are maybe transmitting a different type of knowledge. And this could be made similar to another language. Like, for instance, you name it. It can be everything. It can be German, it can be Dutch, it can be French, Italian, Spanish, you name it. One of the many natural languages. So the arrow at the moment is actually pretty much assimilated to the translation operator. And so if we think of a machine learning architecture that is connecting set of precursors into set of products, then this machine learning operator is nothing more than a neuronal machine translation architecture. So this was the initial intuition. The initial intuition was composed by, number one, maybe there is a language in chemistry. So we don't have a mathematical proof. We have a certain number of evidences, including the one that was published in 2014 by the team of Grisbowski, where they were looking at the statistical distribution of occurrence of functional groups, and then making a parallelism between those statistical distribution and the statistical distribution of occurrence of words in English. And so there are lots of similarities in these distributions. This is one hint. So based on that hint, we said, okay, if there is a language in chemistry, in representing molecules with the Markush representation, then if we use an architecture that has been specifically designed for languages, a neuronal machine translation architecture, we should be able to implement successfully the entire forward reaction prediction task. And so that's exactly what we did. We didn't know what to expect. Instead of using the Markush representation, we have been using a representation which is more friendly for language architectures, which is only composed of alphanumerical characters. In our case, we use miles, but you can run exactly the same type of exercise with selfies, with inches. Of course, the easier is the molecular representation, the more effective is the learning task of the architecture. And in our case, we stuck basically with, we decided to go for smiles. And so we used a data set which was publicly available, extracted from US patent, the USPTO data set, approximately 1 million chemical reactions. And we trained this architecture. Very similar as you would train a neuronal machine translation architecture for translating between English and German, for instance. Many sentences, so many set of precursors and product. And during the training, you are exposing the architecture exactly to every chemical records. So what is the architecture learning? Is learning several things. Is learning to represent smiles. Is learning to extract how the atoms in the precursors are actually mapped into the atoms of the product. And this is one of the things that I will come later towards the end of this short presentation, because you can extract that. And the entire training is completely non-supervised for the location of the atoms. Of course, it's supervised in the sense that we provide the chemical reactivity, but it's completely non-supervised. It's completely transformer family. You can actually get created in 2018 the molecular transformer, which is a specific architecture designed for smiles and chemical reactions. Still today, the molecular transformers are probably the best, if not still the top one in terms of accuracy on benchmark. It was definitely the first one to go beyond 90% of accuracy on a standardized data set. And yeah, we reached basically the very high level in terms of accuracy in learning. Now, we have been looking at the forward reaction prediction. What has that to do with retrosynthesis? Well, let me tell you, if you can build a neuronal machine translation architecture that can translate between English and German, definitely you can build a neuronal machine translation architecture that can translate between German and English. And quite often this requires only one operation, which is invert the order of the data. The reason why this was done in a second step is because there are some normalization actions that you have to do in the data set in order to prepare the data for having an effective learning experience by the transformers. And so very simply, it's nothing more than a transformer, a molecular transformers with the data swapped and properly normalized. Of course, this is a single-step retrosynthesis. You all know when you did your chemistry classes, that retrosynthesis never stops at one step. Quite often, you have to apply the concept of retrosynthesis in a sequence, multi-step. And so what we do, that's nothing more than a tree. It's a graph. What you have to do is nothing more than to explore with traditional methodologies, high-performance computing methodologies. You have to explore the tree of possible retrosynthetic options. Now, the second part, synthesis actions. How does it work today when you have a chemical reaction and you want to compile an experimental protocol to follow in a chemical lab? Well, the very first thing that you can do is to work with similarities. You can search for similar type of transformation in databases, and you can then use your intuition, scientific intuition, in trying to understand how you can adapt the different protocols for the specific case that you have to address. In our case, we didn't want to follow that route. I mean, it's definitely workable, but we were really aiming to have a system that was as autonomous as possible with less human intervention. So we needed to have something that was fully AI-based. And so the very first thing that we did was to compile a recipe book for chemical reactions, organic small molecules. And so even for that operation, because as I said at the beginning or a few minutes ago, we had at our availability a data set of chemical reaction records that was publicly available for training the molecular transformers, but we did not have a corresponding, an equivalent data set of experimental protocols for those chemical reactions. And so what we did was use, again, a transformer architecture for converting humanly readable text into coin-size actions. The coin-size actions are very interesting because they are more easily processable by machines. And I think this scheme, that probably today with all the prompt engineering, LangChain, ChatGPT, could actually be done in a very effective way following a completely different approach. At the time, back to 3 years ago, we had really to follow some steps to compile first a data set and then normalize and put the data set in a condition that was easily learnable by the transformer. So we performed this application of another transformer architecture trained for converting natural language into coin-size actions. And we did that for approximately 1 million chemical reaction entries. So for each of these entries, we had the corresponding chemical transformation together with the mapping operations that had to be performed in the lab. So that's a fantastic data set. I think from a machine learning perspective, you can't hope to have anything better than that. Maybe 1 million was not sufficient. We were always very much concerned during this exercise that the noise and the signal may have been competing each other, and that probably the extraction of the signal from the entire scheme would have not been that easy. But this turned out to be not true. We were able to extract the signal, although in presence of a very big noise that was reflected at the very end in the accuracy of predicting an individual step of a procedure. And so how did it work, the entire problem? We had 1 million of chemical reactions, like the one depicted here, expressed with a language representation. And we were training a transformer, passing in input this text, and matching in output during the training phase the corresponding experimental protocol for this chemical reaction that was converted into coin-size actions and then further generalized. The last step is very important, the generalization, because if you swap the order of the chemicals between the precursors, the result does not change. And so this gave us also a very good way for implementing data augmentation strategies. So being able to increase the data set for strengthening the learning of the model. And this, of course, was a machine learning model, was a transformer architecture. So at the very end, we had one model that was converting every chemical reaction predicted by the retrosynthetic model into actions to be performed in the lab. Now, I want to spend just a couple of seconds on this machine learning model because, in my opinion, it's very fascinating. I find it like one of the amazing things of machine learning in the context of chemistry. So we did not make explicit any context other than spelling out the individual actions that were in the protocol. But we all know that some of these actions, like steering for a certain time or a certain temperature, are characterizing the thermodynamic of the process. If we need to increase the temperature, the process is endothermic, requires energy in order to run. But even other actions like a filtration or the presence of a wash or a phase separation are indication of very precise thermodynamical equilibria. And the filtration, for instance, means that suddenly the solubility of some compound decreased, and that compound precipitated out of the solution. And this is triggering a filtration action. Now, what I'm trying to say is that the fact that a model, a transformer, can actually predict action based on a reaction string, it tells us that the model was able to capture the effect of having specific functional groups in the molecule on the presence of individual actions that at the very end are connected to very precise macroscopic thermodynamic principles. So there was something very fascinating in that, in the fact that the model were actually able to capture that and capture the importance of changing functional groups. What we did at the very end was actually combining all this machine learning model into an experience. So we are scientists. You have seen that the team is very young. I don't include myself into that. The team is very young, and we always wanted to play with technology. And so what we did, instead of leaving the entire exercise at the level of creating machine learning model, we thought, do we think that a machine learning model that is predicting retrosynthesis, is predicting the actions, can actually drive a chemical synthesis on a robotic platform? And this is exactly what we put together. We put together an app, which is, by the way, freely available. So if you are a chemist and you are interested in everything that I presented, feel free to go online, Google for RXN for chemistry, and you can experience these models. But we put together an app where you can draw the target molecule. You have models, machine learning models that help you design the retrosynthesis, the synthesis. You have other models that are helping you design the synthesis actions, including the calculation of all the stoichiometry quantities and solutions that you have to prepare. And then finally, launch the execution on the robotic system and monitor the entire process remotely without being physically present in the laboratory. And how did we do that? Well, the team actually put together some commercial automation hardware. Again, I'm not doing any specific product placement. We have been working with one vendor. And in this case, I mean, we have been using batch reactors. possibility of handling solids and the liquids, together with the one of performing few other operations within this box. There are also analytical instruments for providing feedback, an LCMS, so mass spectrometer, as well as a benchtop NMR. And this is, in essence, we have been having lots of fun, I tell you. We have been placing cameras everywhere, creating that Big Brother experience that was broadcasting 24 hours, including contact mic. So the noise that you hear are actually the noise that you can capture with contact mic from different parts of the hardware. And that's exactly what you can see when you are at home and chemical syntheses are executed on that hardware. This was an extract of 30 seconds for the synthesis of some photoacid generators. We are arriving to an end, but of course I want to give you a little bit what else language model can do in chemistry, and maybe try to inspire you on what else language model can do in any other discipline, whether it's biology, whether it's physics, whether it's mathematics. Because the take-home message from this presentation is that science is something that is reproducible, and we are using in several cases domain-specific language for communicating scientific knowledge. So why not to take advantage of the big revolution on language architecture for actually leveraging the knowledge that there is in the data that we collected in the last couple of 100 years, in which as a humanity we have been applying the scientific method in many, many disciplines. And so another way language models can be very useful is for curating data set. This is a super cool thing. There is a weakness in the machine learning space, which is called catastrophic forgetting. Basically, you train a model, then you try to bring that model into another language, and the model tries to learn the new language, the new records, but it's also biased, heavily biased by the previous learning. And so in order to accommodate the new learning, it tends to forget what the model learned before. This is the catastrophic forgetting. But in reality, you can use this scheme at your favor if you want to clean data set. Let's imagine that you have millions and millions of chemical reactions, and between those you have chemical reactions that are completely nonsense. They don't obey to any specific distribution in chemistry. So if you perform a training and you identify the frequency in which records are learned and forgotten, then you can actually identify the outliers, the wrong grammar chemical records, and then you can really clean up your entire data set, maintaining only the one obeying to the same distribution. You can do more. You remember at the beginning we said language models that take as input text and produce a numerical representation. So far, we have been dealing with language models that take text and convert into text. But if you consider the second one, take text in input and convert into a numerical representation, a multidimensional vector, then suddenly you can build very beautiful things. I mean, chemical reactions are suddenly vectors. And if they are vectors, you can build maps like here. You can use the vectors for training regression models for calculating chemical reaction yields. But you can also extract the entire chemical reactivity that has been learned by the molecular transformers and create an atom mapping scheme that still today is probably one of the best performing, completely unsupervised, again, with very profound philosophical implication at the level of language and chemistry and the combination of the two. We were mentioning at the beginning, we apply this also in the context of catalysis. You can do that for biocatalysis using several representations for the enzymes, starting from enzyme commission numbers. So these are just essentially a way to represent a catalyst. But you can also use the entire sequence of amino acid. And here it comes something very interesting. If you use the entire sequence of amino acid, then suddenly, and you train the model and you try to extract the same concept as the atom mapping, then suddenly what you are extracting is which atoms of the substrate are interacting with which amino acid of the protein. And this is a very a very critical information, because those amino acids in the enzymes are nothing more than making up the active site. So it's really fascinating. Like a language model is actually, by looking at correlation, looking at the attention, long range, short range, is actually capable of extracting three-dimensional information as the one of identifying, given a sequence of amino acid, where is located the active site of the system. So I'm stopping here with few minutes delay, but I wanted to give you a little bit of overview on what is this revolution of language in chemistry, and the hope is that maybe inspirational for applying similar type of methodologies in other fields, from biology, which is very close and nearby, but maybe even to other disciplines like math, like physics, and so on. So thank you so much, and looking forward to a very engaging conversation.
Theo, thank you for a fascinating story. I think you started with explaining the transformer idea, the large language models, on the sort of SMILES notation, and telling us that this is a grammar. But I think you clearly have a vision that goes much beyond just designing the synthesis of a molecule. And I was really sort of intrigued by your SMILES to actions sort of idea, where you say, well, once I have designed the retrosynthesis, you also want to design the actual synthesis that you can then transport in a way to a robot that can carry out that synthesis. So you really want to integrate that whole idea of designing and using the transformer model there all the way up to the automated synthesis. So that's a truly fascinating story. And I'm sure there will be people in the audience or online who have some questions. Who would like to start? Maybe I start by going back to this SMILES to action sort of part, because I think that this, in a way, is almost the most revolutionary part, because I guess the chemist, when you really say, well, sort of where is their skill, their craft, comes into, of course, the actual experimental part, where you say, okay, I think I know that this reaction should work, but how do you actually carry it out? And so how far do you think that your transformer model is in predicting the right reaction conditions? And so, for example, you often have to maybe dilute it a bit, or increase the temperature a bit, or choose a slightly different catalyst. How sort of well do you think the model will perform in those situations?
Yeah, no, that's a very, very good point. And let me say that we do have different type of metrics. Of course, we do have a metric which is purely statistical, and there we know very well that, as a matter of fact, the model in itself is capable of predicting every single action with an accuracy of close to 70%, 67. I don't remember the right number, but let's say close to 70%. This is for every single action in the procedure. Now, you see where is the problem. The probability that you are predicting an entire procedure made up of maybe 10 steps is 0.7 multiplied 10 times, which is an incredibly small number. So you will always have, most likely, some errors in a procedure. Maybe you will have 3-4 errors that you have to really to compile. There is also another thing which is important. In general, we don't experience such a big rate of errors, but because the individual steps are not fully independent. So, which basically means the overall probability is not just a multiplication of the individual factor. And it's very difficult really to, a priori, based on the probability of predicting a single step, to predict what would be the probability of having a step, an experimental protocol of 10 steps completely correct. But in general, this is the bad case scenario.
But this is already fascinating, I think, because I think you're getting very close to what the chemists would do as well when you do this reaction for the first time, right? You don't know all the steps for sure, so you have to try somewhere. But I was thinking, do you ultimately envision that, for example, the system will also say you need some kind of base? I think you showed potassium carbonate on one of your slides. Will the algorithm also come up with suggestions to maybe use a slightly stronger base or a slightly weaker base or slightly different temperature to already predict what will be the optimum conditions? Is that where you ultimately would like to go?
Definitely, this is already, to a certain extent, this is already what, from a training perspective, the system does. Let me articulate a little bit better. The training so far has always been done with positive cases, so positive reactions that have been reported as successful. And so if this happens, you can consider that those chemical reactions are actually the best reported by humans. Now, we can argue whether that's true or not, and I think this is opening a very interesting conversation that goes even beyond machine learning. But when you train a model with positive data, the model is actually trying to fit all these successful chemical reaction in a way that the manifold of the model is actually passing through all these points. And if we assume that those are optimal, then the prediction will be optimal based on the training data. Now, of course, I mean, we all know that unless you have been running a chemical reaction and optimizing a chemical reaction, we are very far from this reality. We know that many chemical reactions reported in literature are definitely not optimal, whether at all reproducible, I would say. And this, of course, I mean, opens up to what you were mentioning. Yes, it's definitely possible to have the model that is predicting an initial sequence as prompting the reaction, but then maybe attaching on top of that different type of AI technologies, like, for instance, a Bayesian optimizer that is further optimizing the entire protocol. So you can think of exploring in a grid space where the elements of the grid are maybe different type of bases or maybe different type of temperatures, different type of conditions, and then apply Bayesian optimizer for actually optimizing the entire chemical reaction. So these are...
Theo, that brings me very close. I have two questions online. Raphael wanted to know when the model is able to suggest better workups than the ones published, and I think that's the question that you were just addressing. But Will Robinson is asking, is there potential for AI dreaming up new synthetic actions? So could it actually come up with procedures that we have actually not used before?
So I'll reply to the first one. To the first one is that in general, the machine learning model can come up with procedures that are better than the published, but for one reason, it plays on the statistics. So you may have you may have protocols, of course, that are very reliable, and maybe you cannot beat those ones. But if you look at the average, the machine learning model will definitely be performing very close to, to the average, if not slightly better. And in essence, definitely you are beating some of the bad reported protocols in literature. So that's for sure. Regarding the second one, it's a very interesting question, and I was smiling because if the intention here is to think that machine learning can maybe win one day the Nobel Prize for chemistry for coming up with a chemical transformation, I think we are still quite far, because all these models are actually operating in a regime where we are fitting data. Now, of course, if we are fitting data in the chemical reaction space, and you are incredibly lucky, maybe you are interpolating between 2 points, and that area was a completely unexplored area. And maybe you are lucky, but I would say that on average, and by the way, you are on your own. You are in a territory which is completely unexplored. There is no data. The machine learning model has learned to connect one part of the space with another part of the space, but you don't really know whether the chemistry is meaningful. So the way machine learning and transformers and these technologies work today, generally, I would say, it's more in an interpolation regime. So we learned how some chemical transformation work. We may not be aware of how they perform when we slightly change the substrate. And so machine learning is actually very useful in that, provided that there is sufficient data for training the models, in telling you how to best run a carbon-carbon coupling or a carbon-nitrogen coupling, for instance. But hard to say that we'll be coming up with the next big chemical transformation for the future. There are very interesting works. They are using slightly different approach at the moment. And so we are all very much looking forward to see what will be coming in the next years, because definitely having technologies that work in an extrapolation regime, so outside of the space where the model has been trained, is probably where the usability of some of this technology will be even of greater impact.
I was just looking at the audience for other questions. There's a question over there. Maybe use the microphone.
Your data set is huge, but you are not sure about how good it is. There can be errors in the data set by fraud or unattended. If you feed back the results of your automatic synthesis to the data set, can you eliminate parts of them?
So absolutely, and maybe for people in the machine learning space that are watching, when I started working with chemical data, I was also thinking, wow, 1 million chemical reaction entries is like a big number. And then you start looking at the truth of who is working on language models. They have billions, tens of billions, hundreds of billions of text. And then suddenly you realize how miserable is the data volume in chemistry. So I'm just saying that to laugh together a little bit on that. But you are absolutely right on the fact that this data set in chemistry are all originating from, and I have to give the credits because I think it's a very important thing, are all originating to one work that was done in 2012 by Daniel Lowy. As a side product of his PhD thesis, he was actually generating some software for text mining chemical reactions from text patents. He compiled the USPTO dataset, but of course, I mean, text mining is a very brittle process because the way humans are representing information in a text is very different. Myself and you are using different styles, are reporting the same information in a slightly different way. So it's very tricky to build a model that actually does a 100% correct text mining task. So this data set, it's absolutely clear. They are very dirty. And I mean, these are numbers that I don't have a proof, I don't have an objective, but I wouldn't be surprised if the amount of wrong chemical records can actually arrive even to 20–30% of the entire data set. Maybe even more, and then would start to be really scary. But let's stop on this 20–30%.
I think it's a very good point. There are some more questions, so I wanted to give them the time as well. But I think it's clear that the quality of the data that sort of we chemists have sort of reported is definitely of a level that can be improved. I see a question here in the front, and then there's a question in the back as well.
Hi, thank you very much for the talk. I had a specific question. So what is the effect of the language representation that you choose on training a model and on the required data to train a model? So if you, for example, represent an enzyme as smiles, does it require more data, etc.? Or how does that scale? And also with respect to the actions that you describe in your model.
No, it's a very, very good point, and even for this one, we will need extra time. In short, it has a very big impact. I mean, smiles have been mistreated by many in general, and I still keep defending smiles for one reason. They are very simple. I'm not saying that we speak naturally the language of smiles, but if you are well trained in smiles, by looking at the smiles, you can already picture the structure that you have in mind. If you try to do the same with Inchi or with selfies or with any other language, it's going to be a little bit more difficult. But because this language have a more complex grammar. So simple grammar, it means that the language model will be doing less effort, will be needing less data for learning the representation, but also for extracting chemistry. And so similar story, if we go from small molecules to proteins, it's very complicated. If you now start going with tokens, with representation of smiles for proteins, first you would be hitting the limitation of the architectures in terms of number of tokens, but second, you would be losing completely the overall description. You would be needing data sets of characterized enzymes that are well beyond the one that we have today. So it's always very important. Language and models are strongly connected. If a language is simple for a model to learn, then you will need consequently less data. And the entire learning task will actually be easier.
Is there a language simpler than smiles? I don't think.
Not that I'm aware of, but maybe you can come up with something. I wouldn't exclude that. I mean, definitely, I think this is the beauty of science. I mean, smiles were actually created back in the 80s. I think I had like 3 or 4 years old when smiles first appeared, and they were created because at that time computers were starting to be very useful for some tasks. This was probably really the beginning of chemoinformatics. And so they were looking for a way to encode structure of molecules in computer programs. And I think that there was a very careful thought in how smiles were put together. So it's one of those examples where humans have been putting lots of brain for addressing technological limitations. Can you imagine a computer in the 1981, 1982, very little RAM, maybe 1 kilobyte of RAM, maybe not even that one. And the net result is that today these things are actually very, very, very useful and very, very effective.
I'm going to give the sort of member in the audience in the back a chance to ask a question as well before we running out of time.
Hello. Yeah, I was wondering what happens if you feed the model a compound that you know doesn't exist, and if you do retrosynthesis on it, does it know that it can't be synthesized?
You can definitely try. Doesn't exist what it means. It means really broken chemistry, like a carbon with 6 bonds.
Carbon with 6 bonds. But what if you have something that is unsynthesizable? So you might have, I don't know, 6 fused 3-membered rings or something. So all the rules are allowed, but it's simply no known chemistry to get you there.
Yeah. This is really speculation. I think that the language models will always try to come up with some sort of suggestion. This is the beauty of the language model. And by the way, you see that even when you use technologies like ChatGPT, the hallucination is coming exactly because the language models do have to produce something. I mean, it's their curse in a certain sense. They have been training for producing something. Now, the good thing is that with every single inference, they also give you a confidence level. And the confidence level is a measure, a mathematical measure of how the prediction is similar to examples that have been seen during training. So I am assuming that an example that is really unsynthesizable maybe is coming up with some ideas. Maybe those ideas are completely chemically meaningless, and this would actually be reflected into having confidence level of 10 to the minus 10, 10 to the minus 15, or close to 0. So that's what I would think the behavior is.
That's clear. Maybe a final question or topic that I wanted to discuss with you. We were briefly discussing this before the start of the of your lecture, and this is maybe more about the future of not so much of chemistry, but of the chemist who is going to do the chemistry or not, because you had a vision where maybe if you wear virtual reality goggles or maybe sensors, then the machine can also learn all the other things that you're trying to do in the lab and could reproduce that eventually, and maybe you cut out the chemist in the end. I wanted to hear your ideas about sort of the future of the chemist.
No, absolutely. So I personally think we are living an amazing time, and I feel like I'm getting too old too soon, actually, for really enjoying all these things. But I can see that like the announcement that Apple made for the augmented reality goggles, I mean, it's coming in a period where we are having a new generation of people that is growing, that is way more open to technology, maybe than my generation. And I think, I mean, there is lots of potential from many technologies to simplify, not necessarily with robotic systems, but to simplify even the operations of individuals in the lab. So you were mentioning video. We do have, I mean, some activities in that space. And if any of you will be at the ACS in August, please pass by. We are planning to have some cool demo to show you how we envisage the blending of this technology in a futuristic lab. So I think that the future is very bright, actually, and it's all about embracing it with the right level of consciousness, and this is applicable even today. I don't think even simply by experience on using language models like ChatGPT, it would be very dangerous to blindly trust at anything that is produced, I mean, by by such a generative language. And similar is in chemistry. Always keep the eyes open, always be critical, but these are tools that are there for improving our productivity.
I think, Theo, that's wonderfully said. And I think, as you mentioned, the future is bright. And I hope there's a lot of young people listening who will adopt many of these technologies, hopefully in the near future. There's a lot of opportunities coming up. Unfortunately, it's time for us. We would like to thank you again for giving a fascinating overview of the work that you have done and your vision for the future. We thank you a lot for that. Thank you.
Thank you for having me with you. Thanks.
And for everyone here, I wish you, of course, a good evening, not before reminding you that next month, on July 11th, we have Andy Cooper in episode number 6, the final episode of the season. And for now, because it's a warm evening, we're going to have enjoy a drink and some further discussion of everything we've heard so far. Theo, thank you again. It was a very enjoyable evening. Thank you.
Thank you. Bye.